Hello everyone, I'm gonna present my project that is called Growth Implementation Considering Prescribed Growth and Several Constitutive Models. So as a brief introduction and for the motivation of my project, tissue expansion is a relatively straightforward procedure in which a silicone balloon is inserted underneath the skin and it is filled with a saline solution during several days, and the pressure induced in the skin basically leads into cell proliferation because the mechanical cues drive some biological signaling that make the cells divide. So in the image you can see a tissue expansion procedure to get extra skin from the cheek of this patient to then replace the nevus or the dark area around the eye. One computational model that as I present here as an example is this from Yoshida and Soderman. They combined and finite element model of a ventriculus, and the growth rate was computed from some cell signaling network from a biological process of the cell that in this case led into cell area increase because they were interested in studying hypertrophy in the heart. So what they did was basically couple the mechanical model and the biological model, from which strain was an output from the mechanical model and an input from the cell signaling process, and then growth as an output from the biological process was the input for the tissue remodeling and the mechanical analysis or finite element analysis. So the purpose of my project is analyze tissue growth considering solid and solid content as a variation in time, along with total deformation changes and its elastic and growth components. How? With the tissue definition of the material cell growth on FEBio, which considers the parameters of osmotic pressure that I will list, plus the addition of new Hookean and Mooney-Rivlin materials of hyperelasticity. So here it is important to recall the strong form of elasticity, in which we have to find the displacement such that this balance over here equals to 0 over the entire domain and is subjected to these conditions right here. So to get the weak form of elasticity, we have to recall that first we multiply this by a weighting function and then integrate it by parts over the entire domain. This would be true for all weighting functions w of x. After integrating by parts, the weak form of the elasticity will be is the one stated here, and from my project I consider the equivalence for the reference configuration. So this is my geometry and my boundary conditions. For these nodes, I consider this one as a displacement when using the cell growth FE biomaterial, and this one when I didn't compute didn't code with this material from FE Bio. And we will see later, but I use this because the cell growth FE biomaterial is mainly dominated by an hydrostatic pressure. So when I used very large deformations, basically my domain or the elements that had high shear stress exploded. I also used this two incompressible definition of this material for the monoribbling and the Newhookian. This is the Cauchy stress of both of them. This is the definition of the cell growth material used in FE Bio. This is the Cauchy stress, where this osmotic pressure is defined by the R and T, R universal constant, T temperature, CR, VR, CE, that you can see the definition below, and the units. So the whole implementation is basically shown here. We have to discretize and then get the residual. For that, we started by a loop over the elements, from which we had to read the nodes of each element, the coordinates, and the reference, and if wanted the deformed configuration. Then we have to loop over the integration points, and since we are using the isoparametric map, it's not just important to discretize the coordinates, but also the Jacobian and the gradient of the shape functions. Here we discretize also the deformation gradient and its transpose. So for analyzing growth in this material, we have to decompose the deformation gradient into its growth and elastic component. And in these cases, the Cauchy stresses will be dependent on the elastic deformation, as you can see here. Then we compute the second Payola-Kirchhoff S, and the balance for this case in the reference configuration is shown here, with the discretion shown below. Also, it is important to mention then that when I couple these two Cauchy stresses of the Newhookian and the monoribbling with the definition of cell growth material in FE Bio, I inserted these load curves from this VR and CR materials of this material in FE Bio and also in the code. This is the discretion of the residual. So here there's one entry missing, but this is mainly the discretion of the residual. And for the change in growth field, I will be following an explicit Euler definition of this differential equation. So first, I'm showing here a comparison of the Newhookian plus the prescribed growth in code versus the FE Bio implementation. From the code results, it is important to notice that the growth deformation and elastic deformation values were very similar. And here in the video. We'll talk about it later. And this is the comparison versus Nehookian plus growth and Mooney-Rivlin plus growth. From those graphs, it is important to understand the following results. With the parameters used for Mooney-Rivlin and Nehookian material, the growth and elastic deformation behaved similar. Although they have different total deformation values, the growth was proportional to the elastic deformation in both cases. In the case of Nehookian plus prescribed growth, also run in FE-Bio, the growth in the program was mostly dependent on the solid increase from the cellular parameters, so every element has mostly area growth without deformation. In the code, the elastic deformation has almost the same range of values that the growth deformation, mainly caused by cellular mass increase.